All right, welcome to Physics Video 2.2. Today we're going to be learning about free fall. I've handwritten the objectives here today. So here they are. You should, by the end of this video, know that the acceleration of gravity is negative 10 meters per second squared for all objects on Earth, and you should be able to apply this concept to problems. All right, so here we go. Before we learn about free fall, we need to learn what a force is. So force, the symbol for force is a capital letter F, is a push or a pull on an object. Examples of forces would include the force of Roy or some other person pushing your object, the force of gravity, force of friction. We're going to learn later on this year about electrical forces. Air resistance, it turns out, is a force. You can picture that if you imagine driving down the car with your hand out the window. The air pushes your hand back, right? So that is a force. Okay, so anyway, we're going to talk more about forces in the next chapter, but you need to be aware of at least that little much. All right. Also, I guess before we move on, it's worth reminding you that when you measure force, you're measuring how hard something is being pushed or pulled. So it says here, if there's a big force on an object, that means that something is pushing or pulling it hard with a lot of force. The goal of a force is that it tries to change the motion of an object. And please note, though, that how much force is on an object has absolutely nothing to do with how fast it's moving. So you can have something going very, very fast with no force on it, or have a really, really big force on the object and not have it moving at all. Okay? Again, that's really something that will become more important in the next chapter when we learn about forces. Okay? So anyway, for now, basically what you need to know is a force is a push or a pull on an object. Okay? I should have listed that in my objectives. All right, so free fall. The definition of free fall. An object is in free fall if the only force acting on it is gravity. The word free fall itself is a little bit misleading because usually you think of the word fall as, and you picture something falling downward. Okay, but it turns out that to be in free fall, that doesn't necessarily have to be the case. All right, so if you drop a ball, as soon as you let go of it, it's in free fall, so that's your first example. It turns out, too, though, that if you throw a ball, as soon as you let go of it, it's in free fall. Because after you let go of it, you're not putting a force on it anymore. So after you let go of it, the only force on it is gravity, and so it's in free fall, which is why these last two examples, here and here, are both examples of free fall. If you throw a ball down or you throw a ball up into the air, as soon as you let go of it, the only force on it now is gravity. And so it's in free fall. If it helps you think of it, when you throw a ball up in the air, why doesn't it go up forever? It doesn't just keep going up and up and up and up. It comes back down because gravity is pulling it down. And since that is, in fact, the only force affecting it, that means that it is in free fall. Okay? So in all of those examples, the only force on the ball is gravity, and that's why they all move down faster and faster, and so they are all in free fall. All right? So Galileo made a really important discovery about this, and he discovered that all objects in free fall are going to accelerate at what's called the acceleration of gravity. Okay? Acceleration of gravity. I'm going to use the symbol A with a little g subscript. A lot of books, most books, if I'm being honest, just use a lowercase letter g. For a number of reasons, I stopped doing that, and I can talk about that more in class. But so we're going to use AG, and it stands for acceleration of gravity. All right? On Earth, it turns out that the acceleration of gravity for all objects is negative 9.8 meters a second squared. Okay? Now, for simplicity, just so that we can kind of get through discussions quicker, we're going to just round that off to negative 10. It's not that I think you can't do calculations with 9.8. It really sort of speeds things along. All right? So for us, from now on, the acceleration of gravity is going to be negative 10 meters per second squared on Earth. Okay? And notice, I don't know why this keeps doing this with the font here. Anyway, so notice the acceleration of gravity is different on different planets. If you go to the moon, the acceleration of gravity is only 1.6 meters a second squared. And on Jupiter, it's much bigger because Jupiter is a bigger planet. Okay? And we'll learn more about that when we learn about forces of gravity. Okay? So, yeah, I think we're good. Cool. Acceleration of gravity on Earth. Anytime you throw or drop an object, there's your acceleration, negative 10 meters a second squared. Okay, that is hugely important. Anytime you throw or drop a ball, that's the acceleration. Okay. Keep in mind, though, that in order for an object to be in free fall, the only force on it is gravity, right? And so what that means is, technically speaking, for an object to be in free fall, there has to be no air resistance. So in the real world, unfortunately or unfortunately, depending on your perspective, there is air resistance. So when you drop a ball on Earth, technically speaking, it's not really in free fall because there's air resistance. All right. That said, we're going to usually ignore air resistance because usually, unless the object is really, really light or moving very, very quickly, air resistance doesn't make a significant effect on the object's motion. Added to that, it's super difficult to calculate the effect of air resistance. There's a ton of variables that affect that. All right. So what that means to us is that if an object is in free fall, which anytime we drop an object on Earth, in this class we're going to assume that it is, that means the acceleration of gravity will be negative 10 meters per second squared, which means, hopefully this looks familiar, every second the object's velocity decreases by 10 meters a second. Okay? So this is huge. What that means is if you drop a feather and a rock at the same time, they're going to fall at the same speed. Okay? Now, on Earth, if you do that, it doesn't work, right? Because the feather kind of floats and the rock drops straight down. But the reason for that is because the feather is so light, air resistance has a pretty big effect on it. Okay? It turns out if you do that experiment where there's no air resistance, they fall at the same speed. When they had the first moon landing, the astronauts did that. They took a hammer and a feather and they dropped them on the moon. And the moon has no air resistance, right? There's no atmosphere. You can't breathe on the moon because there's no air. And so when they did this, what you can see, and I'll show you the video here in a second, both the hammer and the feather fall at the same rate. They fall right next to each other. Okay? They fall slower than they would have on Earth because there's less gravity, but they fall at the same rate. Okay? When I see you in class next, I'm going to do another demonstration to sort of further that, that idea that if you remove air resistance, all objects fall at the same rate. Okay?
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. I have a good picture there. I've got
beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
Superb.
All right, so let's apply this to a problem. Okay, we're going to do a few things here. So we've got three different examples here. We'll call this example 1, 2, and 3. Okay, so in example 1, it says Roy drops a ball from rest. So your initial velocity is going to be 0. That's going to be true anytime you drop something. If you drop something, it starts at rest, so the velocity starts at 0. All right, and then because gravity is pulling it down, that means the acceleration of our ball is going to be negative 10 meters per second squared, which means the velocity is going to decrease by 10 every second. So as the ball falls, the velocity is going to go negative 10, negative 20, negative 30, negative 40, negative 50, and negative 60. Okay? So the velocities are negative because it's moving downwards, and it goes down faster and faster and faster. So that's pretty much what we'd expect, right? When you drop something, it goes faster and faster. That's why it hurts more when you jump off something. The higher it is, the more it hurts, right? Because because you have more time to fall, so you're going faster when you hit. Okay. So second example. Now we're going to have Roy throwing a ball up into the air. All right. Again, once he throws it, as soon as he lets go of it, the only force on it's gravity. So it's going to be in free fall. So here's our acceleration, negative 10 meters a second squared. But this time the velocity starts at positive 30, right? Because he threw it up into the air at 30 meters a second. But after he lets go of it, gravity is going to pull it back down. So it's going to have this acceleration. So the velocity is going to decrease by 10 every second. So started at 30, we're going to go 20, 10, still going up, but it's going up slower and slower until it stops at the top of the path, and then it comes back down. This is just like the ball rolling up the ramp that we did in class the other day. Okay? So, the third example is, what if you throw the ball down from the rooftop? All right, well again, as soon as you let go of it, it's going to be in free fall, so here's your acceleration. So the velocity is going to start at negative 30, right? Right when you let go of it, the ball is already moving down at 30 meters a second, and then it goes down faster and faster and faster, and so on. Cool? All right. So anytime something is in free fall, anytime you drop or throw a ball, automatically your acceleration is going to be negative 10 meters a second squared. All right? So let's take a closer look at that chart in the middle where he throws the ball up into the air at 30 meters a second. So notice, the entire time the ball is in the air, the velocity is decreasing, right? The velocity starts at 30, and then it decreases to negative 30. We pointed this out when we did the ball on the ramp problem. Okay? So even though it's slowing down on the way up and speeding up on the way down, the entire time the velocity is decreasing. Okay? This also points out an important fact, which is this. When you throw a ball up into the air, it goes up and comes back down, it takes just as much time to go up as it does to come back down. It took 3 seconds to go up. It takes another 3 seconds to go down. Okay? Cool. I think that's it. Yep. So I want to reiterate this fact that in this class, anytime a problem is about a ball being dropped or thrown, we're going to assume that there's no air resistance. All right? In the real world, there is. But again, in most problems, it makes a small enough difference that we can pretty safely ignore it. Okay? There you go. We'll see you in class. I don't know.